what does that mean? What is a muscle fiber?
Muscle cell?
It is a muscle cell, right? Okay. So, and this is where the handout comes in that I posted for you guys. So we're gonna fill out that handout. So this is basically just kind of like a one-stop shop for differentiating between the muscle cells. But we have three main types of muscle fibers in the body, okay? And the muscle fibers that you have at any one period of time depend on training. It depends on what type of challenges you give your body. But the different types of cells are characterized by certain items such as how fast the myosin head moves, okay? How fast ATP breaks down, ATPase, breaks down ATP into ADP and PI. Like how fast does that happen? How big is the fiber? Okay, some are larger, some are relatively smaller. What is the primary energy source? Are they mainly using oxygen or they're using glucose? Do they have a good blood supply? We'll talk about myoglobin in a minute. But the handout that I gave you really summarizes nicely the three different kinds and the characteristics that I want you guys to know, okay? So, in the body, we have three different muscle fiber types, and they're listed here. We have what are called slow oxidative, fast glycolytic, and then we have fast oxidative, okay, which is also called intermediate fibers, okay? So we'll go over the first two columns first, and then we'll return back to the last column and describe the fast oxidative, okay? So, just based on the name, all right? Slow oxidative fibers, the speed of contraction, or the myosin ATPase activity, would you say that that's going to be relatively slow or relatively fast?
Probably slow.
Relatively slow, okay? So, slow. What about fast glycolytic fibers, in contrast? Relatively fast, right? Okay, so they're going to contract faster, okay? Now, if we're talking about the primary pathway for ATP synthesis, fibers are either going to utilize oxygen to generate ATP, or they're going to utilize sugar in an oxygen deficient environment, okay? So, again, based on the name, do you think slow oxidative fibers utilize oxygen or utilize glucose for ATP synthesis? Oxygen, because they're oxidative, right? So you can say that they're oxygen dependent, but I also like to call it aerobic. So they use aerobic means for generating ATP, okay? So fast glycolytic fibers, what does glycolytic sound like?
It's using glucose.
Sounds like glucose, it also sounds like glycogen, right, which is a stored form of glucose. So these fibers are not going to utilize aerobic means to generate ATP. They are going to use anaerobic. I'm just going to put anaerobic, and they're using glucose instead of sugar. Sorry, glucose instead of oxygen, okay? Okay, so myoglobin content. Myoglobin is a protein, okay? And myoglobin is a protein found on these fibers that allows oxygen to attach to it. Sounds like hemoglobin, yeah? So, relatively speaking then, okay, if myoglobin is utilized to bind to oxygen molecules, do you think slow oxidative fibers will have relatively high content or relatively low content? If they're oxidative fibers, they utilize oxygen, is their myoglobin content going to be high? Yes. Yeah. Yep. So I'm just going to do arrow up for high concentration. Okay. So fast glycolytic fibers, since they're utilizing glucose for their energy, do they need a lot of myoglobin? Relatively speaking, no. So it's going to be low. Right? So as far as myoglobin content goes, you can also think of it as, if we talk about animals, which we will in a moment, compared to humans, the higher myoglobin content is what's found in dark meat. For example, chicken, okay, versus low myoglobin content is going to be white meat. So myoglobin gives color to the tissue, gives color to the fiber, okay? So dark meat, for example, dark meat chicken, right, is going to have a higher myoglobin content than, for example, the breast meat, okay, which is whiter in color. Okay, that's all based on the amount of myoglobin that those muscle fibers need, okay? And if you think about dark meat versus white meat on a chicken, dark meat is usually found in the legs, right? The drumsticks, the thighs, that's where all the dark meat is, right? And the lighter colored is more in the center of the animal's body, right? So the breast and whatnot. So the legs, slow oxidative fibers are gonna want muscle fibers that last a long time, okay? They don't wanna poop out. So they want more of a slow oxidative fiber, okay, in the dark meat regions of a chicken, that particular animal. Fast glycolytic fibers found in the white meat, in the breast area, closer to the trunk of the animal, you're probably gonna use these muscles, for example, when a chicken has to take flight really quick. Just do something, burst of energy, but it's not gonna last long, kind of a thing, okay? All right, glycogen stores. So, if we said slow oxidative fibers do not utilize glycogen as a primary energy source, are the glycogen stores going to be relatively high or low? They're gonna be low, okay? So they're gonna be low to even no. Super low, okay? Super low. Which means fast glycolytic fibers is gonna be relatively high, right? Because those fibers need glycogen, need glucose to make ATP. All right, what about rate of fatigue? In the name, okay, slow oxidative. Do you think the rate of fatigue is fast or slow? Slow. Slow or low. Okay, so they're slow to fatigue. Fast glycolytic fibers, on the other hand, are going to be quick to fatigue, or fast to fatigue, or have a very high fatigue factor, however you want to describe it. Okay, it's the opposite. Okay, so those are characteristics based on the metabolism and how the fibers operate themselves anatomically. Let's talk a little bit about structure, okay? So for slow oxidative, I already mentioned this to you, this is gonna be kind of the difference between dark meat and white meat in a particular animal. So slow oxidative fibers are gonna have more myoglobin, which is going to give them more color. So we're going to say that relatively speaking, similar to hemoglobin, the color is going to be more red. Okay, so when hemoglobin binds to oxygen, it turns into a beautiful red color. Myoglobin is the same. Okay, so slow oxidative fibers, because they have such a high myoglobin content, they're going to be more reddish in color. They're going to have a nice red sheen to them. Fast glycolytic, because they have low to no myoglobin content, are going to be more white. Okay. So, and we're saying red because there's high myoglobin content, white because there's low myoglobin concentration. Fiber diameter, okay, so it's not really very logical here, but slow oxidative fibers, their fiber diameters are relatively small, okay, in comparison to fast glycolytic fibers, which are going to be relatively large, okay. So the next one you guys should be able to figure out, for concentration of mitochondria in slow oxidative fibers that utilize oxygen to generate ATP, is the concentration of mitochondria in slow oxidative fibers going to be relatively high or low? It's going to be high. Okay, relatively high. Versus fast glycolytic, relatively low, because fast glycolytic fibers use glucose. They don't use oxygen to make ATP, so you don't need mitochondria. Okay, so the next one you guys should be able to figure out too, capillaries. So blood supply to the muscle fiber. Slow oxidative fibers are going to utilize oxygen to generate their ATP. So do you think you need blood vessels nearby?
Yes.
Sure you do, okay? So the relative concentration of capillaries for slow oxidative fibers, we can say is many. There's lots, okay? Whereas fast glycolytic, they don't need them. They're using sugars, so few. Not many at all. Okay. Okay. So now if we go, back to the third column then, we have another fiber that's in the middle, okay? So the third column, fast oxidative fibers, are in the middle of slow and fast, okay? So speed of contraction you can say is medium, right? Primary pathway for ATP synthesis, if they're fast oxidative, are they gonna be aerobic or anaerobic? Aerobic. Mm-hmm. Yeah. Myoglobin content, because they're aerobic, is going to be relatively high, but probably not as high as slow oxidative, so middle of the road. Okay. Glycogen stores are going to be low because they're oxidative fibers. Right? And rate of fatigue is going to be in the middle, medium. Okay. So it's kind of all down the middle for the third column. The color for fast oxidative would be relatively in the middle of red and white. What color would you say that is? Pink, right? Mm-hmm. Pink. Fiber diameter, medium. Mitochondrial stores are going to be high, but not as high as slow oxidative. So kind of middle high, okay, middle of the road. And then capillaries, because they are oxidative, they're going to have a lot, but probably not as many. So probably again in the middle of the road. Okay. So yes.
Can you say one more time for the fast oxidative fibers, the primary pathway for ATP? That's
Aerobic.
Aerobic.
Yeah, because oxidative is in the name. Mm-hmm. Okay. So examples in the body. Or activities that are best suited for these different kinds of fibers. So slow oxidative fibers you want in muscles that you're going to be using constantly, right? That you don't want to poop out. You want them to last a good long period of time, right? So for slow oxidative examples, we can just kind of generalize and say like postural muscles. Okay, so like your back muscles, we're gonna look at these in lab today. Your rector spinae muscle, your calf muscles, right? They keep you walking all day long. They don't poop out. Certainly if you go on a long hike or whatnot and really work them, they're gonna get tired. But on a regular day where you're doing regular day-to-day activities, your calves don't give out on you. That's because they're mainly slow oxidative fibers. Okay. Fast glycolytic fibers you want to use for things where you need a lot of force fast, but you don't need it for very long. Okay? So for fast glycolytic fibers, we can say muscles of the upper extremity. I'll just UE, upper extremity. So your arms. You got to grab a gallon of milk out of the fridge, you can do that. Okay? You probably can't hold your arm out there with a gallon of milk in it for very long because your arm's going to start to poop out. But for you to be able to grab it and lift it and put it on the counter, you can easily do that. Short bursts of activity for fast glycolytic. And then fast oxidative are going to be fibers that you still want a good amount of force. You want them to last a little bit longer. Okay. So we can generalize these and say these are gonna be muscles of the lower extremity, so your legs. Okay, so they can generate more force for a good long period of time, okay? But they may not last as long as your back muscles or your calf muscles as far as posture is concerned. Okay. Okay. So this handout just really summarizes all three nicely. They're different characteristics, where you find them in the body, and again, this topic can be a whole separate class. Muscle fiber recruitment and physiology behind training, you know? So you've got like those guys that do those ultra marathons, right? 100-mile runs, crazy people. Or even century rides, bicyclists that that ride century. 100 miles, a day they do, which is insane, right? So those guys are gonna be super lean, right? They're not gonna have a lot of fat, and a majority of their muscle fibers are gonna be probably combinations of slow oxidative and fast oxidative to get those legs pumping on the bike for those 100 miles. But then again, because they're leaning over on the bike, their back muscles aren't gonna give out on them such that they just collapse and fall over, right? So fast glycolytic fibers, you probably find a lot of those in guys that are training for maybe World's Strongest Man or something. Those TV shows, have you ever seen that? Where they push that giant tire. I mean, they're just like that's all fast glycolytic. Tremendous amount of force, quick power, doesn't last very long, okay? Same thing when, they tie a train to a rope and the guy's grabbing it and pulling. So that's gonna be explosive. It's not gonna last very long. So that's probably gonna be a majority fast oxidative because you're really using your legs to propel yourself forward, right? But you're not gonna last very long. So you need to be able to provide a tremendous amount of force quickly in order to move that train. Crazy. Crazy what the body can do. But just like we've said before, if you don't use it, what happens? You lose it. So if you train yourself to do ultra marathons and then you stop, your body's gonna go back to its resting minimum, right? You're not gonna be svelte anymore. Might put on a couple pounds, kind of a thing. So that's, just what the body does. It responds to training and what you do to it, how you challenge it. Okay, questions about muscle fiber types? That's it for this topic. Okay. Really interesting. Okay, so the last topic then that we need to talk about is lever systems. And we're going to talk about 3 different types of lever systems in the body. But essentially, because muscles, right, have tendons on either end, they usually span across an articulation and attach onto 2 different bones. So bones provide leverage to allow a muscle to contract and provide movement at that joint. Okay, so we consider bones to be levers, and they allow you to do things that physically you wouldn't really think you can do. Okay, kind of like lifting the front end of a car. All right, so let's define the players first. Okay, so we need to know what the 4 different terms mean when we talk about a lever system. Okay, so lever. What is a lever? Well, we're going to define a lever as a rigid bar. Lever is going to be a rigid bar. Okay? Okay. The fulcrum is going to be a fixed point. Okay, so the fulcrum does not move. It's a fixed point. Okay? The resistance is considered the load. Okay, so the resistance is the load, and the effort is the amount of force that's required to move the load. Okay, the amount of force required to move the load. So here you've got a car jack. Beautiful example. The load is the car. The fulcrum is the fixed point, which is the car jack that doesn't move. The lever is the rigid bar that you're going to push down on, and the effort is the amount of force that you're pushing down on to meet and supersede the load, so that you can lift that car, front end of that car up into the air, using something as simple as a car jack. So that's a lever system. So it allows you to do physiological things that typically you wouldn't be able to do. Okay? Okay. So let's talk about the 3 different kinds. So we have 3 different classes. All right? 40 running elephants, don't worry about that for the moment. Let's just talk about each lever class. Okay? A first class lever is here at the bottom left. Okay? So in a first class lever, you have the fulcrum in the middle, you have the load or the resistance on one side, and you have the effort on the other side. Okay? Classic example of that is scissors. Okay, but a great anatomical example of that would be your skull connected to your vertebra. Okay? So the load is going to be the weight of your skull pulling down, okay? The effort is going to be the force required of the musculature on the back side of your neck, which we're going to learn in lab over the next 2 days. Your trapezius muscle, your levator scapulae, your splenius capitis. When you start identifying those muscles, you realize, oh, they all sit in the back of on the back of the neck. So those muscles are required to contract in order to meet the load, okay? And the fulcrum is the joint in between your skull and your first cervical vertebra, right? Your atlantoaxial joint. No, that's AA, sorry, it's your OA joint. It's your occipito-atlantal joint, whatever, you don't have to memorize that, but it's just the articulation between your skull and C1. Okay, the occipital condyle sitting on C1, that's the fulcrum. So your muscles are constantly contracting against the weight of your skull because the weight of your skull is wanting to pull you down. But you don't live life looking at the ground. You live life looking straight ahead, okay, all over the place. Which means these muscles on the back of the neck are constantly required to contract to meet the load and or exceed it. If, for example, you want to look at the ceiling, you got to go above and beyond, right? So if these are postural muscles that we're using all the time, what kind of muscle fiber type are these going to be? Slow oxidative, right? Yep, so some of those muscles are going to be slow oxidative because you're constantly contracting them all day long. And they don't poop out on you. Because if they did, you'd be looking at the floor the whole time. Okay? All right, so that's an example of a first class lever. Second class lever is right next door. So on the second class lever, you've got the load or the resistance in the middle. You got the fulcrum on one side and the effort on the other side. Wheelbarrow is a good example of that. Again, you put a whole bunch of bricks in a wheelbarrow, you can lift it and move it easily because you're using a lever system where otherwise you wouldn't be able to. Okay, it'd be too heavy. But in the body, a beautiful example of a class 2 lever would be the load being your body weight. Okay, so we're looking at your lower leg and foot. Okay, bones we already know. So the load is your body weight. Okay, the effort is going to come from your calf muscles, which again we're going to learn in lab in the next 2 days. Gastrocnemius and soleus, which are the main plantar flexors that allow you to go up onto your toes. Right. The fulcrum. Okay, the fulcrum in this example is going to be the articulation between your metatarsals and your proximal phalanges. So the MTP joint is what we call it, metatarsophalangeal joint. In the foot is the fulcrum. So, beautiful example of a second class lever. You can go onto your toes. Okay, your calf muscles are relatively small in comparison to the rest of your body, right? Most of you easily weigh over 100 pounds. But you can just go right up on your toes, no problem. So your calves can handle that amount of weight with no problems. And that's because of a lever system, okay? So that helps you when you're walking because you're constantly propulsing yourself forward in this motion all the time. And you don't think about it, and your calves don't poop out on you because you're utilizing your metatarsophalangeal joint as a lever system, okay? A second class lever. Okay, so the last one is where you've got the effort or the force required to move the load in the middle, load on one side, fulcrum on the other side. Okay, good example of that is like a, what is it, tweezers to grab something, okay? But a great example in the body is your ability to lift, again, like a gallon of milk out of the fridge, or a 30-pound, free weight, if you want to do a bicep curl. How can you do that? Your biceps, relatively speaking, is quite small. For you to lift that kind of weight, that's a tremendous amount of force that you're making your muscle not only meet, but you have to exceed it in order to move it. So that's a huge, amount of force that you're telling your biceps to do. So in this example, the fulcrum is going to be your elbow, joint. The effort is going to be your biceps muscle because that's the force that's required to move the load. And the load is going to be whatever you have in your hand, whether it's a free weight, gallon of milk, whatever. Okay? You can double it up so you're at Costco and you're getting, a pallet of water or something. Boom. Okay, you can lift a really heavy pallet of water with both hands because of a third class lever system. Okay? So what I want you guys to know is the definition of each and provide me an example and define the parts of that example. Okay? What's the load? What's the fulcrum? What's the effort? Okay, whether you're giving me an anatomical example or you're giving me just a day-to-day example. Okay? Be able to describe each class and give me an example where you define the terms of that lever system. What's what? Okay? 40 running elements is basically just the middle letter, F-R-E, for what's in the middle. The fulcrum, the resistance, or the effort. I don't use that, but if you use it and it helps you memorize where the letters are and what's what in terms of the lever system, you can utilize that. But if not, it's just ignore that. It's not anything I'm going to ask you about. Okay? Okay. Questions about lever systems? Okay. So that concludes what I needed to cover for the muscle PowerPoint. So what's next is integumentary system, which nicely we're looking at in lab today. So all the terms that you're going to hear, we're basically going to look at it again in lab, which is lovely. Okay. Okay. So the integumentary system is your skin, largest organ in the body, and appendages. So other things that are part of the integumentary system that aren't really part of your skin. So like your nails, okay, certain glands and stuff. We'll go over the appendages. Okay, so what do we need skin for? Well, protection, obviously. Skin protects us against the external environment. It allows us to heat up, okay? It cushions our underlying musculature, okay? It can be resistant to abrasions. It protects us against UV radiation, okay? Skin helps retain water, which is important because we're going to talk about burns later. So skin is really good at retaining water, which is something that we need, okay? So we can regulate our body temperature through the skin. So if we need to heat up, we can shiver, and if we need to cool down, we can sweat. So the skin kind of can monitor that and provide whatever we need to do to bring our body temperature back to a more homeostatic level, right? It's all about homeostasis. And then sensory receptors. So we've got light touch, deep pressure, okay, we can distinguish between touch throughout our body because we've got these receptors in the skin, okay? Okay, so what is the skin? The skin is two technical layers. It's the epidermis, which is superficial, and deep to that is the dermis, okay? So the epidermis, because it's superficial, what you're touching on your skin is your epidermis, okay? What type of tissue is the epidermis? Is it simple or stratified? Stratified. Stratified what? Stratified squamous epithelial tissue. Okay, good. So that's the epidermis. Just deep to that is the dermis, okay? The dermis is going to be a layer of connective tissue. So wherever you find epithelial tissue, just deep to that, you're going to find a layer of connective tissue to provide structural integrity and also to feed the epidermis, because the epidermis does not have blood vessels. So the epidermis is going to sneak it from the connective tissue below it. And the dermis is going to be dense, irregular connective tissue. So when you guys were looking at dense, irregular connective tissue in lab, that was in the dermis layer of the skin. Okay. Now the hypodermis is not technically part of the skin, but that's where you have mostly fat. What kind of tissue is fat?
Adipose.
Adipose, connective tissue, right? And so that stores energy. Okay. So hypodermic needles, for example, that's where you're injecting into the hypodermis layer of the skin. That's why those needles are called hypodermic needles. Okay, so let's talk about each layer. So the epidermis. The epidermis, there's a lot of cells that we can find in this layer of the skin. So we know it's avascular, right? It's going to sneak its nutrients and stuff from the connective tissue below. It's got slight waterproofing, which means it's keratinized, stratified squamous. So the four main cells that you find in the epidermis, the number one cell you're going to find are keratinocytes. Okay, so it's the most abundant. And keratinocytes make and maintain keratin, which is a protein that ensures the strength and durability of your skin. Okay, so that's why they're the most abundant. You also find what are called Langerhans cells. Langerhans cells are specialized macrophages, which are white blood cells that basically get rid of foreign particles or trash or debris or things that need to be resorbed. Okay, so they are the trash collectors and protector of anything foreign, okay, that wants to enter. Okay, tactile cells, which are also called Merkel cells, these are cells that house receptors for touch. We'll identify those in lab on a model. And then melanocytes, okay, are not as abundant as keratinocytes, but they make melanin. Okay, and melanin is what protects you against UV radiation. Okay, so you need melanin. Interestingly enough, melanocytes make the melanin, they give it to the keratinocytes, and then the keratinocytes over time break it down. And that's only because you're sloughing off your superficial layer of skin constantly. Okay, so we're just big dust machines is what we are. We're just constantly sloughing things off. Okay. All right, so I'll show you a nice picture of the different cells here in a minute. Okay, so under the microscope and in lab on the models, you're going to identify different layers of the epidermis. And they're listed here from the most superficial at the bottom to the deepest layer at the top. So basally, kind of think of basement membrane, it's like the deepest layer, okay? Now, there's a good mnemonic for memorizing these different layers, okay? Thick skin, okay, stratum lucidum is a layer that's only found in non-hairy skin, okay? Which is also called thick skin, okay? Which is also called cornified skin. Ooh. Oh, hold on. Okay, so non-hairy, and it's also called cornified. The cornified skin slide, you guys looked under the microscope for dense, irregular connective tissue. Cornified means non-hairy. So non-hairy skin is like the palms of your hands and the soles of your feet. Okay, that's thick skin or cornified skin or non-hairy skin. And you only find a stratum lucidum in those parts of the body. Okay? Everywhere else, you'll have the remaining layers, but you will not have a lucidum. Okay, and you'll identify that on the models in lab. So there's a good mnemonic for how to memorize the layers. Okay, and it's based on the first letter of the layer. And it's can, love, get, so bad. Can love get so bad. Okay, that's the mnemonic. And I'll probably say that again in lab. So, can love get so bad? All right. Okay, so here we've got to have the layers reversed. So superficially we have stratum corneum, deepest layer is stratum basale, just deep to that is the dermis. Okay, slightly pink in color, okay, just kind of a reminder that, okay, that's where the blood vessels are, that's where the epidermis is going to get its nutrients and get rid of its waste. Okay. All right, so in the stratum basale is where you find melanocytes. And melanocytes are making melanin. So these gray dots, these are all melanin. And these gold cells, these are all the keratinocytes. So a majority of skin is keratinocytes, right? But like I said before, the melanocytes make melanin and then they give it to the keratinocytes. And what the keratinocytes do is they put the melanin on the superficial surface of those cells to protect you against UV radiation. Okay. All right. So also in stratum basale, you have keratinocytes. This here is an example of just mitosis going on. So you've got a lot of keratinocytes being made and produced, okay, in mass numbers, all right? And they're grabbing melanin from the melanocytes and they're keeping them on the tops to protect them against UV radiation. You also have a tactile cell here, also called a Merkel cell or a Merkel disc, and that has a sensory ending onto it, which allows you to sense light touch. Okay, we'll look at those in lab too. So in the stratum spinosum here, you see a big old Langerhans cell with lots of extensions coming off of it. Again, this is like a wandering white blood cell. It's going to clear up any kind of trash or keep an eye out for anything foreign, okay, that might want to come into this organ, because the skin is an organ. So as the keratinocytes keep being made by mitosis, they get pushed up and up and up towards the surface. As they get up towards the surface where the stratum granulosum is, okay, those keratinocytes are getting super flat, their organelles are deteriorating, and by the time they hit the corneum, they're dead. And stratum corneum is what you slough off. That's what you constantly recycle, because you're constantly making new keratinocytes in the stratum basale. So what you're touching is the dead skin cells that you're ultimately sloughing off. Okay? And again, we'll look at this nicely under the microscope in lab. All right. Okay, so just driving home stratum lucidum, okay? It's only found in thick skin. So palms of your hands, soles of your feet. It's going to be in between the corneum and the granulosum. Okay, and it's called lucidum because it's translucent. It's usually white in color. You'll really be able to see it under the microscope nicely. It's a very white layer. Okay, so again, thick skin, because it has a lucidum, it's going to have 5 total layers. Thin skin everywhere else, so hairy skin, skin everywhere else on the body is only going to have 4 layers because they lack a stratum lucidum. Okay, enough about epidermis. So the dermis, just below it, lots of blood flow, good amount of nerve supply, okay? Because there's blood flow, we can regulate temperature, okay? The hide of an animal, so your leather jacket that you love, that's the dermis of that animal, okay? And there's 2 different layers to the dermis. Question: if you get a tattoo, what layer of skin is a tattoo imprinted on? Why? So tattoos have to be imprinted on the dermis of the skin because you're constantly shedding your epidermis. You don't want to spend hundreds of dollars on a nice tattoo and all of a sudden it just starts to slough off on you. So tattoos are imprinted on the dermis of the skin. Okay. All right, so the dermis itself has two layers, a papillary layer and a reticular layer. This whole layer here below the epidermis is the dermis. The papillary layer includes these bumps that are called papilla, okay? So the papillary layer is right where those little indentations are, okay? And the papillary layer is areolar connective tissue. Now, because the dermis has these little bumps, we call those dermal papilla. And on the opposite side, the epidermis has these indentations that the papilla nicely fit into, kind of like a puzzle piece. So it keeps the epidermis nicely situated on top of the dermis. It's a nice snug fit. That's what we mean by corrugated cardboard. It's kind of like that cardboard that you, when you open up a box, you see the padding. It's similar. Epidermal ridges are basically just the indentations on the epidermis that are fitting right on top of the dermal papilla for that nice puzzle piece fit. Okay? And just FYI for fun, the dermal papilla are what give you your fingerprints. So everybody has different dermal papilla orientations, so everybody's fingerprints are going to be different. Okay, so the remaining majority of the dermis, okay, not in the papilla, but below it, the rest of it is considered the reticular layer, so it's a good 80% of the tissue. And that's going to be your dense, irregular connective tissue that you're looking at. Okay. Okay. So in this layer of the skin, you can get stretch marks, and stretch marks happen when those collagen fibers get torn, either from trauma or maybe excessive weight gain. Females that are pregnant, they can get stretch marks on the side of their belly. That's typically where, that's the layer of the skin where you're going to see that kind of damage, okay? It's the collagen fibers. And we already know that it's very vascular, it's very innervated, and we have lots of hairs in hairy skin that penetrate through the dermis, and we'll identify those in lab. So what surgeons do is, because of the amount of fibers in the dense irregular connective tissue, they can look for lines of cleavage, which is how the collagen fibers align themselves, kind of like the creases in your palm. They look for, you know, lines on the skin that they can follow so that when your skin heals, you get less of a scar and less adhesions, okay? Because you're going along the grain of the protein fibers. Okay. So, hypodermis, mainly fat, okay? Hypodermis is designed to anchor skin to underlying musculature. All right, we'll really see that when we dissect the cat this week. Okay. Hypodermic injections here, still very vascular. Again, there's adipose connective tissue, so we've got a lot of blood supply. And because it's fat, it's a good insulator. Okay, so it can regulate temperature. The formal name is telesubcutaneous, but we're going to know it as a hypodermis because it tells you exactly where it is, deep to the dermis. Okay, so appendages of the skin, okay, are just little smaller players, really. So hair, nails, sweat glands, oil glands, okay. Oil glands are formally called sebaceous glands. As far as a nail goes, the only thing I really want you to know is kind of the root of the nail, which is called the lunule, okay. The cuticle is called the eponychium. That's just the formal term. The body of your nail is what changes color. It looks more pinkish, and that's because you have less protein fibers, so you can see the blood, the vasculature underneath it. okay, versus the root, which is very thick, that's why it's white. And then you've got your free edge of your nail, which is what you trim. Okay? That's it as far as appendages go. We'll identify sebaceous glands and sweat glands on the models in lab. We'll also identify the different components of a hair, okay? So the deepest part of a hair is called the bulb, okay? And in the bulb, we have cells that are undergoing mitosis to make more hairs, okay? The root of a hair is what penetrates below the skin surface, okay? So the root is below the skin surface, but once you pass the surface of the skin, it becomes a shaft, okay? So if you're shaving your shaft of your hair, okay? Now you guys can, I'm not gonna ask you about medulla cortex, keep going for it. You don't need to go into that kind of depth. Follicle, we're gonna look at in lab, but it doesn't matter to me that you know two different layers of it, okay? So just follicle is fine. So follicle is like a covering that covers the bulb and the root below the skin. Okay, so the follicle is kind of like this little covering here, and it's deep, okay? So, what's better for prolonging hair growth? Shaving or plucking? I should say, which one grows back faster, if you shave or if you pluck?
Shave.
You shave, right? Because you're shaving at the shaft. If you pluck, right, you're attempting to pluck from the root, from the bulb, out. So the next time you pluck a hair, look at it. You'll be able to see at the distal tip a black dot, which is where the bulb is. You'll be able to see a little gelatinous covering, which is the follicle, okay? And unfortunately, even if you pluck it, the cells, okay, are still gonna maintain some sort of presence in the skin. So even though you pluck it, it's gonna grow back, right? So that's why people do, you know, laser treatments and all that to ultimately kill those cells and prevent hair from growing back. Okay, erector pili muscle is what allows your hair to stand on end, for example, when you're cold or when you're scared. So do we have voluntary control over this?
No.
No, okay, so it's gonna be smooth muscle tissue. It's not skeletal, and it's certainly not cardiac, because we're not talking about the heart, so it's gonna be smooth muscle. Okay. And again, it'll be muscle tissue that has some sort of lateral connection to the hair. So when it contracts, boom, it moves the hair. Okay, as far as glands go, okay, the main ones we're gonna look at in lab are gonna be the sweat glands and the oil glands. Okay, sweat glands are also called sudoriferous glands. There are two different kinds, okay? And again, we'll identify these in the models in lab. Merocrine is everywhere on your body. Hairy skin, non-hairy skin, you have it all over the place. All right, when you're at the gym working out, your merocrine glands are working overtime, all over, okay? And the sweat that comes out of a merocrine gland is usually mostly water. Okay, there's a little bit of salts and stuff in there, but mainly water. It's mainly water-like fluid, right, which is sweat. Apocrine glands, okay, are found in different areas of the body. Okay, so they're found in your armpits. They're found in your groin, okay? And the fluid that is secreted from an apocrine gland is slightly different in nature. It has more of a higher protein content than water. And so what it does is it associates it with some sort of an odor, right? So apocrine glands are gonna be found in parts of the body where you carry some sort of odor, and that's because of the material that's being secreted from those particular glands. The way I think about it is apocrine glands, apes are hairy. So you're gonna find them in your armpits, you're gonna find them in your groin. Okay, so that's apocrine. Sebaceous glands are oil glands, okay? They're typically directly connected to a hair, which we'll see under the microscope, okay? but they're usually under hormonal control, okay? But not necessarily. I mean, when you go through puberty, you have acne on your face and everything, and you know, oily skin and all that. That's an example of the hormonal control of your sebaceous glands. But like, you know, oily hair glands, that's not necessarily something that's under hormonal influence. Okay. So the other two that we don't really look at in lab, but I want you to know, are ceruminous, which are glands that are found in the auditory canal. What do you think those glands secrete?
Earwax.
Earwax. And again, earwax in modified amounts is designed to protect you. It's designed to protect particulate matter from entering your body through your ear canal. So the next time you take a shower, don't go crazy with the Q-tip, okay? Be gentle, right? It's all about moderation. My dad had a tendency to, gosh, he was just a wax collector, man. And it started to affect his hearing, I could tell, because the volume on the TV would just slowly go up and up and up and up, and I'm just like, ah. So I would take him to the doctor, they'd look in his ears and say, oh boy, yeah, you got a lot of wax. I'm like, what causes that? Like, is it just, you know, somebody, it's not genetic, is it? And they're like, no, you know, it just depends on the person. So there are times when there can be an excess that may affect your hearing, in which case, okay, you may need to go to the doctor and get it irrigated. Every time we did, the volume of the TV went down. So it was well worth it for me. All right, and then mammary glands are modified apocrine glands, okay, because mammary glands, when a woman is pregnant, are going to secrete milk. So again, higher in protein content associated with odor, so they're basically apocrine glands that you find on females. Okay, almost done here. So oil glands secrete oil, or what's called sebum. Okay, so all you really need to know about oil glands is that if an oil gland gets infected, it can cause a pimple. Okay, we've all had pimples. Pimples, you've got undergrounders that are red, they hurt, okay, there's a sign of inflammation, there's a sign of a potential clog, okay, which could be a whitehead, okay. If that infection gets oxidized or exposed to oxygen, then that material can harden and become a blackhead. Okay, so you can have whiteheads, or you can have blackheads, or you can have inflammation starters, which are those undergrounders that hurt so much. Right? That's all you need to know about oil glands. Okay? Don't worry about holocrine secretion. We're not talking about secretion methods here. Okay? Okay, next slide. Axe. We're not going over methods of secretion. Which leads us to the last little bit of information, some pathologies, okay? So one major pathology in skin is burns, right? A lot of people think that infection is the #1 worry or concern with burn patients, but infection is not the #1 cause. Does anyone know what is?
Dehydration.
Right, it's fluid loss. Fluid loss is the #1 reason. Okay, because again, skin is a water preserver. So if you lose that, then you're going to lose the ability to retain water. And that can be life-threatening, because if you lose water, you lose blood volume. And if you lose blood volume, what happens to blood pressure? It goes down, and you're in some serious trouble, okay? So that's the #1 concern, okay? Infection is second. eScar is just the term they use for burned tissue, so when they're doing wound care on a burn patient, okay? But the 3 pictures show you the difference between a first, a second, and a 3rd degree burn, okay? So a 1st degree burn is like a sunburn, okay? And a 1st degree burn is the epidermis layer of the skin only. Okay? So you've only penetrated the epidermis layer of the skin. Usually just treat it with aloe vera lotion and get out of the sun and let it recover. Okay, but it is a burn, so anyone that's had a sunburn and you go in the shower under hot water, it hurts because it's a burn. Right? Okay, so a secondary burn is where you've got all of the epidermis and the upper 1/3 of the dermis. So this is a little bit more intense, you probably get some blistering, okay? Both of these conditions are called partial thickness burns. Okay, because you're only partially going through the top two layers, okay? A third degree burn is epidermis and all of the dermis, okay? And that usually requires some sort of skin graft, and those are called full thickness burns. Okay. Okay, so last bit of pathology here, obviously, is skin cancer, one of the things we're not immune to here in Southern California. So there's 3 different kinds of skin cancers that you can get. My dad had both, the first 2 that we're gonna talk about. Thankfully, he didn't have melanoma. But basal cell carcinoma and squamous cell carcinoma are very, very common. I mean, dermatologists are gonna be employed for life here. I mean, they have just a permanent growing population of patients, because as you get older, you really have to get your skin checked and make sure you attack things early, right? Early detection is key. So basal cell carcinoma is the least malignant of all 3. So it's got the best prognosis. And usually they'll kind of scoop it out, you know, check and see if the margins are all clear. And then just essentially stay out of the sun or wherever it is, whether it was on your scalp or on your arms or shoulders, you know, no exposed area to the sun. Squamous cell is a little bit different. Again, it's just a different cell type. It doesn't matter, you don't have to memorize what layer of the skin each of them is from. You know, just basal cell has the best prognosis. Squamous cell does too. So they'll scoop it out, check and see if all of the borders are clear, okay? They may recommend radiation or special creams. So my dad had both because he was, I mean, when he was younger, he would mow the lawn, be outside doing gardening and stuff, and he would maybe wear a hat here and there. Ever since I've taken that man to the dermatologist over the course of his lifetime, I don't leave the house without a hat. I don't leave the house without face sunblock. I don't leave the house without making sure, like, okay, if it's really gonna be hot, I'm probably gonna spray my arms too, and my legs. So it's that important. So they recommended radiation for his squamous cell carcinoma, but at his age, he was approaching 90, and I'm like, you know, I really don't want any kind of side effects with him. Already, because he was just showing some signs of memory loss and such, I just didn't want to throw that into the pot. So we decided, nah, we don't need to do radiation at the moment. So, and he was fine. But he did have quite a large procedure on his scalp called a Mohs procedure, which again is very common. I learned all this from the dermatologist. Just take a giant scoop out of his scalp of potential squamous cell carcinoma. Again, all to protect anything from spreading. So, poor guy, he always just looked like he came back from, I don't know, it's almost like auto mechanics school in a dermatologist's office, because they've got all these little bells and whistles, and they've got the lights shining down, and before you know it, you walk out of there with like all these Band-Aids on, and they're like, here's the cream, and whew, yeah, it's a lot. But he took it like a champ. Okay, so melanoma is the worst, all right? So it's where the melanocytes turn bad, which is not good. Okay, the ABCDs is the American Skin Cancer Society of basically just keeping an eye on changes to your skin. So anybody light and fair skinned like me, or that has a history of moles, which I've gotten from my dad, you know, you gotta keep an eye on them and have a dermatologist look at it too, because they see it every day, and they can spot things that, you know, I can't see something on the back of my thigh, I don't know what's going on, you know. So you just gotta take care. If there's something unusual, something you're not sure about, it's better to go in and get it checked. I've heard stories of dermatologists being out in the community, and they see people like at the grocery store or something, they're standing behind somebody in the grocery store and they see a lesion, and they go up to the person and they say, you need to get that checked, like right now. Like scary stuff, like oh my gosh. So, yeah. Take care of your skin. Again, largest organ in the body, wanna make sure that it doesn't go askew on you. Okay. Okay. All right, questions? We've cut it just shy of good, half hour break for you guys. Get some sunshine and some